Hello guys, welcome back to another video. So I just found my recording laptop, so which means we can actually get back to making videos. No, just kidding. Actually, I just got busy because Turing started a few weeks ago, and yeah, basically work got in the way. But now we're back. So uh, we have two problems here from the MIT integration B, both from 2024. Here you can see that the integration limits are the same, but the integrand are just quite similar, but totally different. And you'll notice that one is placed in the qualifier, while the other one is placed in the regular season, meaning that one is considerably harder than the other. And you will see why as I go through both problems. So if you would like to try these problems on your own, you can pause the video now. All right, so let's get started. So for this one, I'm going to first do the left one, the left integral first. So this integral features an infinite tower of fractions where in the numerator you have x and in the denominator you have 1. In the numerator you have x plus and then the power the what is it the tower starts again with x as the numerator and 1 as the denominator. And then the loop continues in all four instances of these triple dots. So if you want if you want to see more of this, it's something along the lines of it's x plus and then x plus something over 1 plus something. And then here you have x plus something um, over 1 plus something, and so on and so forth for each of these dots. Now, to solve this integral, it will be nice if we could simplify the integrand first. And for these types of infinitely recurring pattern on the integrand, the usual strategy is to assume something to be uh, is to assume the repeating unit to be something. So here we can see that the entire integrand is repeating itself. So we can assume that x plus something over 1 plus something all over 1 plus x plus something over 1 plus something here is equal to t. Okay, so you can see that the entire integrand is t itself, but the second, what is it called? The second time it repeats here, we can replace them with t, which means all of this is equal to x plus t over 1 plus t equals t. We can multiply both sides by 1 plus t to obtain x plus t equals t plus t squared. These t's cancel out, and then we have t equals square root of x. Actually, it's plus minus square root of x, but because the integral goes from 1 to 3, which is always positive, we have to pick the positive sign. So that's why here we can just assume that t is equal to square root of x. So what that means is the entire integrand is simply square root of t. And this integral simplifies to something very simple. So this is the antiderivative of square root of x is 2/3 x to the power of 3 over 2. And then we insert the integration bounds. So that means it's 2/3 times 3 to the 3 times square root of 3 minus 2/3 minus 1 square root of 1. And then we have 2 square root of 3 minus 2 over 3. Pretty simple. However, the same cannot be said for the second problem. All right. The second problem features something quite similar, an infinite fraction tower, and the integration bounds are also similar. In fact, they're equal. However, the result of simplifying this integral will be different from that of the first one. So the strategy will be the same. We just let the repeating unit be t. So this is 1 plus 1 plus something over x plus something all over x plus 1 plus something over x plus something. If you let this be equal to t, that means this expression on the left becomes 1 plus t over x plus t. It should be equal to t. That means this is equal to 1 plus t equals xt plus t squared. And now you can see where this is going. T squared plus x minus 1t, well, where I move the t to the right-hand side, and then 1 here should be moved to the right-hand side as well, equals 0. And then there's a quadratic in t, which means to solve it, we can use this, you can use the quadratic formula. So a is equal to 1, b is equal to x minus 1, and c is equal to negative 1. So that means t is equal to x minus 1 plus minus square root of x minus 1 squared plus 4 all over 2. And again, a plus minus arises here, but we just need to take a look at the integration bound. It can be shown that uh, because this entire integral is equal to t, and we want x to be between 1 and 3, that means we pick the positive sign. So t is x minus 1 plus square root of x minus 1 squared plus 4 over 2. So that means I'm going to copy this just so that I don't have to write it all over again. This is equal to the integral of x minus 1 plus square root of x minus 1 squared plus 4 all over 2. So this becomes this one. Now, this integral has two parts to it. One part on the left, which is x minus 1, and the other part on the right, which is the square root of x minus 1 squared plus 4. The left-hand side, or the first two terms are easy to integrate term by term, while the right-hand side is a bit of is somewhat of an integral that you usually find in university level calculus courses, for which you need to find a trick to do it. Okay, we're going to start with the left one. So you can separate the integrals. So this becomes x minus 1 dx plus 1/2 integral of x minus 1 squared plus 4 from 1 to 3. And I'm going to abbreviate this as, say, I. So the left side is simply 1/2 of 1/2 x squared minus x from 1 to 3. And then here this is I. And now we have 1/2 of 9 over 2 minus 3 minus 1/2 plus 1 plus I. So this is, let's see, 9 over 2 minus 1 over 2 is 4. Minus 3 plus 1 is minus 2. Right? Plus I. And then this is 1 plus I. I hope you don't mistake 1 and I here. Okay, so we got the left integral taken care of. What about I? Well, I is a bit more complicated. So recall that I is equal to 1/2 of the integral of x minus 1 squared plus 4 from 1 to 3 dx. So for these types of integrals, you will have to do a trig sub using the uh what is it called again? Using the substitution, or rather using the property that tangent squared x plus 1 is equal to secant squared of 1, secant squared of x. So based on this, we will let x minus 1 be equal to 2 times tangent of theta. Because we're doing a trig sub, we will have to change the integration bounds. So if x is equal to 1, that means tangent of theta is equal to 0. And then when x is equal to 3, tangent theta is equal to 1. And that means on both sides here, we have this is going to be all right. The first one, theta is equal to 0. The second one here, they should be equal to pi over 4. Okay. So I is equal to 1/2 of pi over 4, 0. Oh, also one thing. Because we're doing this substitution, that means we will also have to change dx. So dx here is equal to, if we differentiate both sides, we get 2 secant squared theta. So this becomes 4 tangent squared theta plus 4 times 2 secant squared theta d theta. All right. So the integral, the integrand can be rewritten as, we can factor out 4 out of the square root. And then that means we have 2 times square root of tangent squared theta plus 1 times 2 secant squared theta d theta. Now, you can simplify this. This is just secant of theta. And then you can also multiply all the constants together. So that means just got 2 in front. Here we have secant cubed theta d theta. Okay, so at this point, that means we will have to evaluate the integral of secant cubed theta. There's a trick to this. Well, the first trick here is to use integration by parts. So we can rewrite this as the multiplication of secant squared theta and secant theta. And then notice that secant squared theta is a derivative of tangent of theta. So that means this is 2 times, oh, sorry. 2 times tangent of theta secant theta, while taking the values between 0 and pi over 4, minus 2 times the integral of, so we have to write tangent of theta here, and then we have to write the derivative of secant of theta. If you already know the derivative of secant of theta, it is secant of theta times tangent of theta, d theta. All right, let's evaluate the left side. The left hand side becomes 2 times 1 times square root of 2, and then, so it's like 2 times 1 times square root of 2 minus tangent of 0, which is just 0. And then minus 2 times the integral of tangent squared theta, secant theta, d theta. Now, we reuse the integration, oh sorry, the identity that we just mentioned earlier. So this is equal to 2 squared of 2, 2 squared 2, minus 2 times the integral of secant cube theta, secant cube theta minus secant of theta, d theta. Yeah, because you moved the 1 to the right hand side. And then we can simplify it further just to make it easier to see. All right. Oh, there's a plus. Now, notice that the middle term here, the integral of secant cube theta appears again. But we also need to take care of the last term, which is still quite difficult. So I'm going to write it here, just so that we can substitute it later. So first of all, the integral of secant of theta, d theta, if you've watched my previous video, you will know that this is equal to the natural logarithm of secant of theta plus tangent of theta. And if we plug in the integration bounds, then we get this. So that means this is ln of secant of pi over 4, which is square root of 2, and then tangent of pi over 4, which is 1, minus natural logarithm of the secant of 0 is 1, and the tangent of 0 is 0. So this is natural logarithm of square root of 2 plus 1. All right, so if we rewrite this entire thing again, this becomes all this. Okay, so now notice that here we started with 2 times the integral of secant cube theta. So that means we can rewrite this again and then equate it here. So here. Right. It's right there. Now, what exactly are we looking for? We're looking for this itself. So that means if we add this integrand to both sides, we get 4 times pi 0 from 0 to pi over 4 secant cube theta d theta plus 2 square root of 2 plus 2 natural log of square root of 2 plus 1. Right? Because we only need 2, we can divide both sides by 2. So this is the answer. Okay, and then don't forget that 2 times the integral secant cube, secant cube theta d theta is exactly the value of I that we're looking for here. There you go. So that means this is I. So if we assemble the results from the first and second parts of this integral, we get that where is it? Ah yeah, we get that the result of this integral here is a combination of 1 and I. So if we re oh wait, hold on, that's not 1, is it? It's -1. Should be -1. Oh, yeah, you're right. I'm sorry. There's a negative sign here. Okay, I forgot. It's minus b plus minus b squared minus 4ac over 2a. Okay. It shouldn't really affect okay, it wouldn't affect the hard part. It only affects the left part here. So all you need to do is just to change x minus 1 on the left side into 1 minus x. There. So 1 minus x. So that means this is, yeah, this is just, you simply reverse you simply multiply the result at of the left side integral by -1. Okay, sorry about that. So 3 minus 9 over 2 minus 1 plus 1 over 2, 2 minus 4, -1. There you go. So, okay, it doesn't change the entire result. So it's just -1 plus square root of 2 plus natural log of square root of 2 plus 1. There you go. A little bit of hiccup right there, but overall, I caught it. Did you get both answers correctly? Let me know in the comments below. So I guess that's all for today, and I'll see you next time. Bye.